For making the time to talk today with us.
No problem. So yeah. Um,
Hey, hi, Adebayo.
Hi. My
hello.
hair's like rough right now, but yeah, I was gonna tell you that I'm moving to Nigeria for my research. This
Oh,
are any of y'all in Nigeria or nah?
Fortunately, I'm
no,
not. I mean, I wish I was, but I'm not.
Okay. And my sister took a job at Okra, so we're gonna be living together.
that's
In
But,
so
but
good.
Yeah, so super excited and
I'm so excited that this is finally happening for you. You've been
Mhm,
trying to get to the country.
mhm,
what
mhm.
what will you be working on?
So I'm doing research on the tech ecosystem. So I'm getting my PhD in anthropology. So I'm more like an academic, but I want
Hmm.
to write about what is happening, like write a book about it. So
Nice. What
coming
so
from a
what would
different.
be the subject of your book?
So I'm going to be looking at computer village and tech startups. I'm really interested in like technopolitics. These are like academic terms, right? So
Yeah, yeah,
technopolitics,
yeah, sure.
platform economies, and I'm just interested in how engineering is happening in Nigeria as well.
Okay.
So, yeah. But generally, I think more needs to be published about what's happening. So,
Yeah,
I mean, I
absolutely.
know you have the journalists publishing what they're publishing, but
Funny thing is that Julius and I were just discussing the problem we currently have in Africa. Let's stick to Nigeria at the moment. That there's a lot of things that are undocumented. Is
mhm,
heavily interested in data collection. So we're just talking
mhm,
about this, and you
awesome.
are also looking to document more of this
Mhm,
technology. What's
Yeah.
going on
yeah.
on the continent in the country. I think
Or
it's
even
really
stay,
awesome.
to be honest.
Mhm.
I'm so over America. We can talk about this later.
I know, right?
Yeah.
We have about 1 minute. It's okay. Hi.
Data collection is very important. If you're
Yeah.
interested, if you want to include that as well, that would be.
Uh-huh.
I'm always
Nice,
like pushing for things like this.
nice to meet you, Julius.
Nice to
I'll
meet you as
email
well.
you. You're
Okay.
at MIT, right?
Yeah.
I'm at Princeton. So I'll
Ah, okay.
email because
Okay.
I was planning to reach out to you anyways to talk to you about like your research and how you're thinking about algorithmic colonization because that's the narrative that's popular
I
right
see.
now.
I see.
Yeah.
Sounds
So
good. Yeah.
Okay. So we're right on time. Hi everyone. Welcome to another edition of AISST Lagos Colloquium. Today we are very privileged to have Julius Adebayo with us. So he's a PhD student at MIT in electrical engineering and computer science. He's interested in developing methods that enable ML-based systems to exhibit reliable behavior when deployed. In particular, is interested in constraints related to interpretability, bias, algorithmic fairness, and privacy. Is also interested in data collection, especially when it comes to ways to reliably estimate the Nigerian population. And today, Julius will be talking about challenges with debugging ML models with post hoc explanations. Thank you so much, Julius. It's a huge privilege to have you join us. And the floor is yours. Please take it away.
Okay, great. So yeah, feel free to interrupt at any point to ask clarification questions or any questions you have. So the plan is to make this interactive if possible. Okay, so to start, I thought I would give so she read the like official bio that makes you sound impressive, but I thought I'll actually just sort of give an idea of where I'm coming from. So right now I'm doing PhD in computer science and mostly focused on machine learning, and I've been sort of thinking about causal inference lately. But so I came to the US in for college. So I spent most of my primary and secondary school education in the Loring actually, and I grew up in the Loring even though my parents are from Kogi State. And if we have some time later on, we'll actually discuss um, Teju said, I'm very interested in data collection and things like this. And a lot of that goes back to listening to my parents talk when I was young, because I always ask them questions about Ilorin, and they will, most of the time, people always answer questions with like anecdotal experience of like, oh, I think our population is 2 million or 3 million or whatever. And I just found that the lack of data about questions you might have in Nigeria is very interesting. So we'll get back to that later. But so let's talk about some sort of machine learning research now. So I'm sure everyone on this call has heard, deep learning models are being applied basically all over the place. And you might have seen papers or reports that deep learning models are outperforming radiologists in a variety of different tasks. And so here's like two examples. So here you have like a radiograph, and the task will be for you to sort of say, what is the age of the person whose radiograph this is? And then here, this is a knee x-ray. And then the task here would be sort of knee arthritis, and to discover and to identify the grade of the knee arthritis that this person might have. So these are like two examples of tasks that you might do in radiology. And the reason why this kind of task is sort of high stakes and important is because imagine you train your deep network on this data sets, and then you take it to a clinic and you say something like, all right, my deep network has a performance of whatever, 99% on a validation of test sets. And so this clinic should start using it for their, to like diagnose new patient age or knee arthritis. The first thing they'll ask you is, how do we know that the model that you trained? So this I'm sort of showing this F data as a model. How do you know that this model is reliable? How do you know that it's doing the right thing that you want it to do? And so that's sort of the motivation behind a lot of the work in interpretability and sort of reliability in machine learning. And the reason why that is a problem is because there is a big issue with spurious correlations. So, and I'll say what that is shortly. So there are two sort of big open problems, I think, with deploying this kind of models now. One of them is that it's possible for your model to learn the wrong associations in your data sets. The other problem is that, let's say you train your model on hospital A or data sets from hospital A. Then if you take it and you want to apply it with images or x-rays from hospital B, your model might not perform well. And you might not know ahead of time that your model is going to not perform well. So these are like two big open problems. So to actually sort of drive this home, this example is from this paper by Bagdeli et al. From 2019. And what is interesting in that with it is that, so they trained Inception v3. So if you do like deep learning research, I'm sure you know, Inception v3 is one of the classic architectures. So they trained it on this kind of hip radiographs. And the goal of that model is you should be able to figure out if this person has a fracture or not. So it was a binary classification problem, and they were trying to figure out whether that person has a fracture or not. And what they found out, so they trained the model was very accurate. So this is like a schematic of the model. And they found out that the model was relying on the scanner type that took the radiograph. Instead of actually diagnosing hip fracture, the model was relying on the scanner type that took the radiograph. So, so think of it as something like, let's say you have a hip fracture. They take you in and they take your x-ray on one machine. And then what might happen might be that if they want to then confirm that there's really a fracture, they might take you to the next more high-grade machine and then take your x-ray again. And so a lot of the people that have hip fracture maybe might get x-rayed twice and get x-rayed by like the really strong machine. And what happened here was that the model was just trying to classify which x-ray imaged a particular hip, which is not what you would want. And so something like this is like very pervasive in machine learning, especially image classification or even text classification. And you usually will want to recognize that your model is relying on the right signal. So the spurious correlation that I just described is one example of a bug. So This kinds of problems where your model is relying on the wrong thing in the machine learning pipeline, there are sort of things you can call bugs within machine learning pipeline. So here's like the standard supervised learning pipeline in machine learning. You have a set of inputs, you feed them into a model, and then the model will say something like, this radiograph is 10 years old. And there are different errors that can happen at each stage of this pipeline. So here I'm sort of just showing different errors that might happen. So you can imagine that, let's say there might be labeling errors in your input. So when you're collecting your data from the hospital, it could be that maybe the person entering the label for this input, instead of entering 10 years, they ended up entering maybe 17 or 16. And so that can be like a labeling error. You could have the spurious correlation issue that I described before. Another one that can happen at the model stage would be, one issue that happens when you want to deploy a model is that you can have an error in or a mistake in your code where you might accidentally freeze a layer, or you might accidentally reinitialize the weights at a particular layer. And we'll get back to what this reinitialization means later. Another one, and which is also a big one that I mentioned before, is sort of out of distribution inputs. What this means is that, like I mentioned before, you have, let's say you collect radiographs from hospital A, and then you train this model on data from hospital A. Now you want to apply this model on hospital B. There's currently no sort of good theory or good guarantee that you can give that this model will perform well on data from hospital B. And so these are kind of like, you can think of them as like bugs, and similar to how there might be a bug when you're writing like a normal program. So these are bugs that can also happen with like a machine learning pipeline. And ideally, these kinds of bugs are things you would want to avoid. So in this talk, we'll actually only look at these two, the labeling error and the reinitialized weights. And when we get there, I'll sort of say more about what those are. And like I said, feel free to stop me at any time with questions. So given that there might be bugs in the machine learning pipeline and you want to sort of identify those bugs, there's a big field of interpretability in machine learning. And the goal of that field is that you want to be able to sort of produce artifacts from a model that explains to a human, a person, what the model is relying on, why the model is making its decision. So for example, let's say I've trained one of these deep learning models. So here, that's what this F data is representing. I then feed in this radiograph, and it says this radiograph is 10 years old. So one question I might have is, what are the parts of this input that are most important for the model for it to classify this input as 10 years old? So this kind of a question is one question that is sort of well studied in this field of interpretability in machine learning. And one way that people answer this question is they generate something called a feature attribution map or a saliency map. And what you should think of this as, this image is the same as this image. And what this image is showing is what parts of the image the model is relying on to sort of make the prediction that this image is a 10-year-old person. And so the really highly highlighted white portions of this image are the parts of this input that the model is mostly focusing on to make the prediction. So you can think of this as like a feature importance heat map or feature attribution or saliency map. I'll mostly call them sort of saliency maps for this talk. Okay, so in the rest of the talk, actually, I'll just, instead of using those radiology images, I'll use these bird images, because birds are sort of more, I guess, more easy to sort of reason about here. And so if you want to sort of generate a saliency map for this, it'll also look like this. So here, ideally, let's say you trained a model that's on, so think of this, and maybe this is like an image, a model trained on the data set ImageNet, or a model to do animal classification. So it gets the input of this bird, and you wanted to say, okay, what is the object in this image? And it says it's a junco bird. So those predictions are supposed to be like the actual predictions from this model. and it says it's a Junco bird, you can then ask, what are the most important parts of this image that the model is relying on to make the classification Junco bird? And then you get this image. So there's the feature attribution and saliency map methods, they will generate this image for you. And if you get this image that sort of highlights the beak, the eyes, and sort of parts of the bird, then if you, as a person that trained the model, is looking at this image, then you say something like, oh, my model is really relying on the parts of the bird to actually classify that it's a Junco bird. It's not relying on some other thing. And so maybe my model is doing the right thing. And with the radiology task as well, you will say, okay, the model is actually focusing on the hand. So I can sort of be rest assured that, okay, the model is like doing the right thing. And as you most likely see in the rest of this talk is the takeaway basically would be that the methods that generate this kinds of images, they are not as trustworthy as you should expect them to be. And I'll clarify that later on. So are there any sort of clarifications, questions, or any other comments that people want to offer so far? If not, then I'll keep going. But as usual, you can stop me anytime if you have clarification questions. Okay, so you might be wondering, so why are these saliency maps sort of interesting, and how can they be used for debugging a model? So let's say you get this image of a wolf or a husky, and then you feed it into the animal classification model that we have, that we've been using so far. And the model says it's a husky. I actually don't know what husky, I'm not very good with like dogs and animals. So I actually don't know what a husky is, but this is a classic example in this literature. And this is the reason why people develop this method. So let's say the model says this is a husky, and then you say, generate a saliency map for me to say, what are the most important parts of this input that the model is looking at to determine that this input is a husky. So you then get this image. And so the gray here is sort of like the model is not relying on the gray parts of the image. It's mostly relying on this parts. And what you'll see is that the model is actually relying on the snow in the background to determine that this image is a husky. And so this is a kind of a spurious correlation that I mentioned, where because all the images of huskies in the data set that this model was trained on, all of them had a snow background. So the model basically learns to identify snow with husky. And so what it'll do if you show it, and if you pass in an image of a snowy background, it'll just predict that it's a husky, which is not what you want your model to do. And so this is the kind of thing that you would hope a saliency map can help you identify. And then ideally, you collect additional data of huskies that are not on snow background. And then you can fine tune your model on that, and that will fix this problem. So this kind of a debugging loop is what you ideally want a saliency map to help you with. And that's sort of the inspiration behind why a lot of these methods are sort of developed. Okay, so this is the sort of the section of the talk that might have a little math. So if you don't really like equation and math, you can pretty much zone out in this part. This is more for somebody that's really interested in these methods and wants to sort of know how these things are computed. So you can think of the model here, this F theta thing. You can think of it as mapping a vector to a vector. So it's mapping a vector. So this image, you can represent it as a vector in RD. It's mapping this image in RD to RC. So C is the number of classes here. And then the actual prediction, the logit predictions, you can think of them as, so class Junco bird or class husky or class dog or whatever. You can think of it as, it's a function that is mapping from this input all the way to a single scalar value. And that's important because the way you actually calculate this heat maps is you take derivatives. So you take the derivative of class Junco bird with respect to the input. And if you sort of think back to calculus, what a derivative tells you is how much do I change a particular dimension of my inputs to change the output. So what this is like a fancy thing for gradients of, this is sort of telling you the gradient of f of I with respect to x, and that will give you something that's the same size as this as the input, and then you sort of visualize that input. And these two papers are sort of where this idea came from. And so what that tells you is, it tells you the sensitivity of your model with respect to the input dimension. So if I go in and I change, so an image is like a sort of, this can be like a 290 by 290 by 3 image. So if I go into it and I go to like a small dimension here, and I change that dimension by, let's say, epsilon, or I change it by 1, or I change it by 2, how much will my prediction Junko bird change? That's what this is telling you. And so that's sort of a measure of importance. And if you do a lot of like TensorFlow, PyTorch programming, or automatic differentiation programming, you realize that this thing, you can just, it's like a one-line call in any one of this automatic differentiation packages. So that's why these ideas are very, very common. And if you visualize, so I just talked about the gradient before, right? If you visualize the gradient, this is what you see. And as you can see, it looks very sort of visually incoherent. You can't really see the bird. So it's not clear what's going on in this image. So what happened was, because of that, people created more additional methods that sort of to be more visually appealing than the gradient. And what this method is called smooth grad, sort of smoothing the gradient. So what it does is, you take your input and then you create, let's say, n copies of the input, and then you add Gaussian noise to the input, and then you compute your gradient, you average it, and then you get an image that looks like this. And as you can see, this looks like almost what you would want to have compared to this image of, which is this, you can't really see the bird here, but when you do this method, you see the bird. So to sort of conclude this section, there's now like a huge class of saliency approaches. So if you're in this field, you've probably heard of Lime, SHAP, but each one of these images is a different way of computing the saliency map for this input, for the prediction Junko bird. And as you can see, all of them look slightly different. Some of them are clearly showing the bird, like this one is actually sort of nailing exactly what the bird looks like. Some other ones are basically looking like noise. So let's say you're the person that trained this model, and then you want to sort of use an interpretability method to sort of inspect your model to see what are the parts of the input the model is looking at. If you go to like a GitHub, an open source GitHub repo that implemented all of these different methods, how will you know which one of these methods to pick to interpret your model? And so, because there are sort of no theoretical guarantees for most of these methods, and it's not clear if you're the person that actually came up with this model, which one of these methods will you use to try and understand what this model is predicting? So the focus of this talk actually is on trying to understand which one of these methods is effective and which one of them is not effective. So here, I think I'm showing maybe like 12 or maybe 15 different saliency map methods. And we want to know if you're training your deep net on an image data set or a text data set, which one of these methods should you use to be able to sort of understand your model, and which one of them is reliable and which one of them is not. So that's the sort of the key question we're going to talk about here, which is what this slide is saying. And so in short, what this slide is telling you is that, as I'll sort of go into shortly, most of these methods are not reliable, and they're actually not as effective as they look on first pass. So we'll come back to this slide, but it's sort of like a summary slide of what will the actual results that we'll see later on. Okay, so let's look at the first test we'll apply to this method. So just to remember, what we want to figure out is there are 17 or more saliency methods. And you and I, after we train an animal classification model or a model in radiology, we want to know which method should we use. So our first test would be sensitivity to model parameters. So let's say you train a model. We'll call this model Model 1. And this model has 90% performance on a test set. And then I take that model, I completely reinitialize the weights on the top layer. And that is Model 2. The first model gives a prediction Junco bird. And because I've reinitialized the weights of this model, it gives prediction dog. So what we ideally want here is, if I compute the saliency map for this model, it should be different than the saliency map that I get if I compute it for this model. And that's what this is trying to show. So the test that we'll actually do is, we'll take this model, we'll reinitialize the weights starting from the top layer all the way to the bottom layer. And basically, we're trying to destroy all of the things the model has learned. We want to completely mess up the model. And ideally, a model with with reinitialized parameters, you should have a different saliency map from a model that was trained normally. So this model has 90% performance on a test set. This model has 50% or random performance on a test set. The prediction is wrong. So it's predicting dog on this image, which is a bird. So we expect the saliency map should be completely different, and it should be essentially garbage. And what we'll find is that it actually isn't. For some models, what we'll find is that this saliency map it's actually sort of it looks like what the original model gave. So what this is showing is, so this is the original image, and we're going to look at something called a guided backprop saliency map. This is a specific kind of saliency map method. And what this does is, you can then take inception V3 and reinitialize the top layer. So completely reinitialize all the parameters in the top layer to what you had at the very beginning in training. And then you compute the saliency map again, and you get something that looks like this. So what this is saying is that this method, guided backprop, is giving the same saliency map on a normal model as it does on a model that I've reinitialized the top layer. And then you can keep going. You can reinitialize again. And now the prediction is actually off. So this is it's a species of a dog. And so now you've reinitialized both the top layer and the second to the layer after that. And you can keep doing this for guided backprop. And what you will find is that you can reinitialize almost all the weights in guided backprop, except the weights at the lower layer. And the guided backprop saliency map will look almost identical to what the normal saliency map is, which means this method is essentially trying to reconstruct the input, and it's not really explaining what the model is doing. It's just trying to sort of approximate what the input is doing. So it's not telling you what the model is relying on. It's basically trying to do edge detection on the inputs. So any questions or any sort of clarifications or comments that people might have? If not, I'll keep going. But as usual, feel free to interrupt me. So you can then, like I mentioned before, you can do this reinitialization that I just explained for a bunch of different. You don't have to try and understand what's going on here, but this slide is telling you that we did this experiment for 17 different methods. So all of the methods I told you about, and then you can compute a similarity between what the original model is doing with what the model is doing after you've reinitialized the weights of the model. And sort of what you will see is any line above this black line is basically not an effective method. So if we go back to this image that I showed you earlier, so these are all of the different saliency map approaches that I showed you earlier that you can use to explain this animal classification model. So this test that we just did ruled out all of the ones that have X's on them. So This one that has a question mark is essentially saying that depending on the parameters that you use for this method, it might pass, it might not pass. But all of these methods that have X's on them are sort of methods that are not sensitive to the model parameters, which was one of the questions that we wanted to answer. So if you are now going to that GitHub package that has all of these methods implemented, you know to not use these methods for your actual computing the dependency maps because they don't actually rely on the model parameters. Okay, so that's sort of the takeaway from that sensitivity analysis that I mentioned. Another thing that we can do, so I'm sort of coming towards another test, is so remember at the beginning of the talk, I mentioned how they're all different kinds of bugs that a machine learning pipeline might have. And you might want to use an interpretability method to understand what bugs a model might have and what bugs it might not have. And so here is another kind of bug. So the bug here is that you have mislabeled examples in your training set, and your model is learning the wrong label for those images. So what this is showing is, imagine I train model 1 where this bird input, it had the correct label. So in the data set, the label was bird. And then imagine a different data set where this bird input was mislabeled. Instead of the label bird for this input, it was labeled as dog. So this row is you're explaining a model that had the correct label. And in this row, you're explaining a model that had the incorrect label. So the model thinks this thing is a dog, and this model thinks this image is a bird. Same thing for this dog. The model thinks it's a dog, and the incorrect label says this is a bird. And so what these visualizations are showing is that, so at first glance, the top row looks very sort of visually identical to the bottom row. And for most methods, some methods not quite. So some methods like this is basically noise. But if you look at the gradient, it's sort of highlighting similar parts of the image. It's sort of focusing on similar parts of the image, even though the label for this is correct, and the label for this is incorrect. So what this is telling you is that you can't use these methods to differentiate between a model that has learned the correct label from a model that has learned the incorrect label. Because if I show you this image as the explanation for this model, you'll say, oh, it's relying on the right parts of the image. If I show you this image for the model that's the incorrect label, you will also say it's relying on the right parts of the image, even though the prediction is wrong. And so the sort of takeaway from here is that while these methods are visually interesting, they show visually interesting parts of the input, you can't use it to sort of differentiate a model that has learned the correct labeling from a model that has learned the incorrect label. And so, which is another problematic issue with this sort of saving CMAP approaches. So this is the second bug that we tried to use this method to identify. So the first bug that we did was the sensitivity, and we found that a majority of those methods were not effective for sensitivity. Here, for labeling, so this is mislabeled examples. We're also finding that pretty much most of the methods, except, so you can sort of rule out some methods, so decomnet, pattern net, but basically 90% of these methods are also mostly ineffective for differentiating a model that has the correct label from a model that doesn't have the correct label, which is very problematic. And the reason why, so to remind you again, the reason why we're doing this is because in the literature, a lot of these methods are very popular for trying to understand your model. So there's this pervasive problem in deep learning of, you train a deep network, you just have 10 million weights, and you don't understand what your model is really sort of reliably doing. And the goal of this method is to say, this is your model that has 10 million weights. This is what the model is relying on to make its decision. And what this is saying is that, hold up, this is actually not the case. And a lot of these methods might actually not be as effective as you expect them to be. Okay, so as with any talk, you're supposed to sort of talk about related work. So I'm coming towards the end of the talk now. And so I wanted to sort of highlight some other things some other papers in the literature that have looked at this question and have sort of made also similar contributions. So the first one is this paper by Six et al. So if you remember in here, I sort of mentioned that all those methods with X's are not sensitive to the model parameters. And by not sensitive, it means you can reinitialize the weights of this model and the visualizations that this method's produce are still similar. So in the paper that we wrote that sort of has all these results, we didn't actually explain why that is the case. So why do those methods fail that particular test? And we just sort of, we gave a generic explanation, but we didn't actually explain theoretically why that is the case. And this paper by Six et al., it was at ICML last year. They actually sort of theoretically explained why those methods fail and what is it about those methods that make them invariant when you change the parameters of the model. So this is a very good paper that sort of theoretically explains that. Though there's still some open questions. So if you're interested in this line of work, this is one paper to look at. Another one that is sort of highlighting some problems in this area is this paper by Alvarez and Mellis. And the point of that paper was that they're showing that a lot of those saliency map methods are unstable, meaning you can change your input by a little amount, and the explanation you compute from the saliency map methods will actually change by a big amount. So I can change my input a tiny bit, but my explanation changes a lot, even though my model doesn't change and the prediction of my model also doesn't change. And that's another problematic issue with a lot of these explanation methods. So the last sort of paper I wanted to highlight is this paper by Chu et al. This was also from last year. I think this might have been at NeurIPS, I don't remember. And what they did was they actually did a user study with Amazon Mechanical Turkers. So they showed Amazon Mechanical Turkers saliency maps of different kinds of models. So a strong model, a weak model, or a model that is relying on spurious correlation, or a model that is not relying on spurious correlation. And what they found essentially was that the saliency maps were not effective for helping the Amazon Mechanical Turkers to actually debug the model or sort of know if a model is reliable or not. And this is also another problematic issue. And so these are sort of three generic, not generic, but three papers in this literature that are also sort of highlighting something similar to some of what I've discussed. The work in this literature is actually very extensive. And this is just 3 out of probably hundreds and hundreds of papers. But these are 3 very interesting papers that are saying things along the lines of what I presented. So that's why I picked these 3. So go back to the summary that I promised earlier. So we're coming back to the end of the talk now. So even though nobody has said anything so far, there's actually a discussion at the end of this talk, so you'll be forced to actually say something. There's a reinitialized, so we talked about the reinitialized weights bug and then the mislabeled examples. So the reinitialized weights bug, we found that there are some class of explanation methods that are invariant to the higher layer weights of these deep networks. And then in mislabeled examples, we found that the saliency maps that you get from a lot of these methods are sort of visually similar, regardless of whether the model has a correct label or the incorrect label. We also did some user study experiments, but I didn't really discuss that here because that will take too much time. And then the results that we got were very similar to the results of Chu et al. that I mentioned earlier. So I think the spirit of, so this is my last slide actually before I get into the discussion. So the spirit of this talk has been very critical of saliency approaches. So if saliency approaches are not the right way or not, they're not sort of effective for model debugging, what might be a method that might be effective instead? That's what this slide is starting to show. And there's starting to be work along this line in the literature. So the sort of key idea here is that you should develop models that are intrinsically explainable by themselves. And so I've tried to sort of show that schematically here. And this is based on these 3 papers by these 3 authors. And if you want, I can send you pointers to this. But the idea is that in the traditional sort of machine learning or deep learning literature, you take your image data set and you just fit a CNN on it. You just train the biggest convolutional neural network that you can find. So 10 million parameters, 60 million parameters, you just train it end to end on this data set. Instead, what this line of work is proposing is that instead of just training your CNN on these images, you should also enforce interpretable concepts. So you should enforce that your model should learn interpretable concepts along with the CNN. So imagine this is your entire architecture. So you have like the lower layers that the regular CNN, so you can use whatever CNN pipeline you want there. And then at the upper layers of your model, you force it to sort of learn interpretable concepts. So for this image data set, so let's say you were trying to classify what this bird is, what species of bird this input is. What you will do is you force your model to learn beak color, beak length, wing color, undertail color. So things that are sort of human interpretable concepts, so that when you want to actually debug your model, if you're an expert in bird classification, you can sort of look at the output of this layer in your model and use it to actually figure out whether your model is relying on the right concepts, which would be beak color, beak length, wing color, to determine whether the species of input is a bird or not. And the idea would be that, so the idea that how you would actually do debugging in that case is you would take this architecture. So I'm calling this architecture SCDNN, so self-explaining deep neural network. You take the architecture, and the architecture itself, it spits out this concept vector, or you can think of it as a concept vector, which is for each one of these things, how important are they? And then you're the domain experts, you then go back and forth and sort of try and understand how the model is behaving. So imagine this was a radiograph, like we talked about in the beginning of the talk. And then this will be something like clinical variables that a radiologist understands. And what would happen is this person would be a radiologist, this person would be the model. The model will spit out a concept vector for the radiologist. The radiologist can then look at the concept vector and say, okay, the model is relying on the right properties for it to sort of identify the different parts of this of the image that are actually reliable. So this idea is still it's a promising idea for sort of model debugging, especially because model debugging is very important in domains like radiology, healthcare, places where you actually need to understand what your model is doing before you use it to make predictions on people. So that's sort of the big takeaway along those lines, that it's possible to do better model debugging when you consider self-explaining deep neural networks. So that's sort of the takeaway. So let me pause here for any questions on the talk, or any comments, what your thoughts are. Before moving, so we're going to move into something completely different on like data collection in Nigeria after this, but okay, this is sort of the end of the talk. Yeah.
Thank you so much, Julius. And I think Adebayo has a question.
Yeah, can you guys hear me?
Yes.
Okay. Thank you so much. This was very interesting and accessible actually for someone like me, that doesn't have a technical background. I was just wondering, I know you said that one of the papers you cited goes into how the original models were trained and why you need saliency maps and all this type of debugging. But I just had a question about the input part. Like, were they just the data they were feeding, were they just feeding images, or they would somehow code those images and feed lines of code in place of those images? And the reason why I'm asking is these like interpretable concepts, like who's going to come up with it, and like what's going to be the standard, and how is that going to be fed into? Because I could see similar issues happening.
Yeah, that's a good point. So yeah, in the training pipeline, you do feed the images. So what you do is you convert this to like a long vector that looks like this. So you convert this into, so this might be like a 224 by 224 by 3 RGB for like red, green, and blue. And you then convert it into like a long vector, or you can have it in that shape. And you usually do some pre-processing on this. So you might like normalize it, or maybe sort of flip it up and down and do different kind of things. And then you feed, that's what you then feed into the model to then do the classification. So in terms of, so that's the first part of your question. In terms of where do these concepts come from? So that's actually a very good question. In general, and this is still open, this is something that's still sort of ongoing work in this area. Right now, this concept would come from the domain experts. So if this was bird classification, this concept would come from somebody that has looked at all the images of birds and said, okay, this bird, the beak color is whatever this color is, gray or pinkish something. The beak length is this. The wing color is gray. The undertail color is this. So there would be like a bird expert that will go through millions of images and actually sort of annotate each image with specific concepts that each of those inputs have. And then the way you would then train it is, normally you would train it by just feeding it only the images, but now you will feed it the images and the concepts that domain expert came up with. So that when you are then get a new input, so imagine you train your model that way. If you then get a new input, you would then ask your model, so if you get a new bird, you then say, all right, model, tell me what are the concepts you relied on to make that this input is a bird. It'll then give you a bird and you can compare it to what the domain expert said. Of course, the big issue here is that you're asking the domain expert to go through thousands or millions of images to then label all of those images in a detailed manner with concepts and then feed those images into your model, which is essentially unrealistic, but that's sort of the state of the world right now. So I'm anticipating that there will be a lot of papers this year, next year, that will try and address this concept issue, which is that right now, to get these models to work, you need, if you have 1 million images, you need somebody to have gone through those 1 million images to sort of annotate all of these concepts for those 1 million images, which is mostly unrealistic. So, but there are ways you can do to sort of reduce that burden on a domain expert. And that's what I'm sure future papers are currently working on. But does that answer your question?
Yeah, thank you. I just hope AI scientists are thinking critically about who they're designating as domain experts, because like an immediate problem I can already identify is like the problem of color blindness, and large populations don't see color the same way. So you have to, in your cross section of domain experts, you have to like make sure that you're incorporating those like factors.
Absolutely. Yeah. So the word domain the phrase domain expert here is hiding huge there are a lot of huge problematic issues there. And actually there's starting to be a new field that is looking at that, not as much as I would want, frankly, but it's a huge problem, and I have no good answers for
just wanted to bring points out for conversation. That's all.
No, that's definitely valid. Good point.
Thanks, Julius. I just have a quick question. So
Sure.
if we already have all of this concept here,
Mhm.
can't we just like perform the normal machine learning, like fit a logistic regression or something on it?
Great question. Great question. Yeah. So that's a fantastic question. So why not just, if you have all these concepts already, why do you need the CNN? Why not just train a logistic regression on the concepts? That's a great question. So the first answer is that so there are two ways to answer that. The first one is, and given that you have this question, I would definitely say this paper partly answers that question. But the first answer is that you might not have all of the concepts that you need. So in this image, you might only be able to label beak length and wing color. And that might not be all the concepts that you need to be able to sort of classify this image as a junco bird. So that there might be some other concepts that you expect your CNN to learn that you've not gotten your domain expert to label. So in that case, you would have, so here I've sort of annotated each one of these things to have a concept, but you imagine that you have extra indices of this vector where you haven't labeled the concept, but you've sort of asked the model to learn those concepts by itself. The other part, so that's the first part of the answer, which is, it's kind of problematic because so let me get back to that. But so that's the first part of the answer. The second part of the answer is, empirically, what this paper actually found was that if you just train the logistic regression model on this, it's not on only the concepts. It's not as accurate as if you ask your CNN to learn some more spatial features and sort of embeddings. So combining the CNN for this concept is more accurate than just training a logistic regression or SVM or something on this human interpretable concepts. But you shouldn't be satisfied with the answer I just gave, though.
Yeah.
That's a general, because it's still an open research question with how do you, if you're able to collect, because if you're able to collect reasonable or good enough concept, then you shouldn't need this. But by definition, you will not be able to do that because there are probably going to be some interactive concept that you're not able to collect. There are going to be some other concept that you want your CNN to learn. So you're sort of doing a hybrid, and you're hoping that because you're imposing this structure on your model is able to get less crazy. Because what happens if you just use a CNN is the CNN basically learns whatever concept it wants. And when you impose this structure on the CNN, you're asking it to say, sure, learn some other concept, but I want you to for sure learn this set of concepts. So I want you to for sure learn the beak color, the beak length, the wing color, and all of these other things. And then you can learn some other stuff if you want. But if you don't impose this structure, then there's no guarantee that the model will actually learn this concept.
Yeah, just a quick follow-up. Thanks for the answer. So how you'd train this is that you just concatenate these concepts with the input, right? And just feed it to the CNN. Or
so you can do that, or the way that is actually more that this paper did it was so imagine you have like a ResNet or whatever architecture you have. You take the last layer of that and you force it. So your inputs is this image X, the label Y, and this concept vector C. And what you do is you force some layer in your network to predict this concept vector. So your loss function will have, it depends on how you set it up, but your loss function you take the output of some layer in your model, and then you force it to also be the same as this.
So ultimately, you're not concatenating. You just like have some of these layers. Just make sure that you map to this, and then continue the training loop.
Exactly. So the title of this paper is Concept Bottleneck Models. And so imagine you map to a concept vector, and then from the concept vector you map to the output.
So we can think of it as an embedding.
Exactly. It's a concept embedding layer, basically. And what this, though I actually haven't, I don't know. So I think they might have tried it if you concatenate it with this input, but then you're not really forcing your model to learn. So if you concatenate it with this input, it's possible for your model to completely ignore that vector and still rely on the input.
I see.
If you use some middle layer, you're forcing your model to actually absolutely learn those things.
Thanks for all of the great answers.
Yeah.
Do we have any more questions from the audience?
Hey, Julius. Hey, everybody.
Hi,
Yeah,
Mikasumi.
so my question was, do you think the domain expert should really have a grounded knowledge of machine learning to be really productive in this process? Because, you know, I was reading an article about human in the loop, about including humans, about including experts in in the process of creating this model. And also, is the variance really worth it? Like the difference between a model training on data without the domain expert, is it really that much different than machine learning engineers just making their own models? Do you think it's worth it for a company to employ a domain expert?
That's a very, that is the $1 million question. This domain expert question is one of the $1 million questions in this slide. I agree. So I will say everything I'm about to say right now is my own personal. I think there's not enough. There's probably not enough yet to go one way or the other in this question, and it probably depends on the domain you're in. So if you're a startup that is doing, so what I'm about to say, I actually don't believe it, but this is what people say all the time. So my view is that you should have a domain expert all the time, especially with these DNN models, because they just learn a lot of wild things, and you want somebody that knows enough about the task and knows enough about what should be the realistic thing a model should learn to be able to sort of look at it. You also mentioned the fact that should a person know machine learning and also be a domain expert? Ideally, but basically you're asking for a unicorn, right? So let's say you're doing bird species classification. You're asking for somebody to also know in detail about bird species and also be able to train a ResNet on like all of these images. Ideally, that's the person you want. But most of the time, I'm guessing you can have the person that's training the model also sort of talking to the person that actually knows all of the general concept. But to your point on the domain expert, so the general sort of line that a lot of people say in ML is that if you're not in a high stakes task, then it might be fine not to have a domain expert. So if you're a startup that is just doing your startup is to take in images and do bird species classification for like a conservation or something like this, then if you get a bird wrong, then nobody's life is in danger, right? So there's no issue if you make an error in that case. But if you're so you could argue that maybe you don't need a domain expert, even though I still think you probably do, because in any task, if you want to know that if you train a model and your model is making the wrong decisions, then you have to be able to go in and figure out why the model is making the wrong decision. So you need to sort of have sort of higher surface level of domain experts. But if this is radiology, which is why I used the radiology example, if this is the radiology example and you want to deploy this in like a clinic to be able to decide whether somebody has knee arthritis or not, hip fracture or not, then for sure you want somebody who has expertise in that thing to be able to try and sort of figure out if your model has learned the right thing, is your model making the right predictions, is it making the right predictions for different subpopulations of people, or is it making the right decisions based on the right concept? So I think, so my personal opinion is you most likely need a domain expert all the time, though I don't think this is probably a popular thing in machine learning. But the question of when and how you incorporate the domain experts, if they're machine learning experts or not, this is all very important questions. I think ideally you want the person that can train the model and also understands the domain. But most of the time you can't find that. So you try and sort of talk to people or get the domain experts to like sort of, you show them what your model is predicting, and ideally you show them explanations, and hopefully they're able to give you insights.
Thank you, Julius. I was watching a video yesterday about how SageMaker ground truth uses domain experts in collecting their data. So from the initial stage, you know that okay, this data is like they kind of have like an end goal then in collecting their data. And I know that's part of what Amazon is working towards. They are trying as much as possible to automate the whole process. I also know some companies like Scale AI. Well, that's for big companies because you said that earlier. Like I mean, it depends on how high stakes the situations are. So like I know people really serious about this stuff. Really incorporating domain experts in their life cycle.
Yeah. I think it's, and I guess this is where there's a like disconnect between the people that are writing the papers and the people that are actually using these models in practice and in the real world to actually do things. And so if you're like in a university, it might be more difficult to find a domain expert, or because you're not even, your model doesn't really have to work if you're writing a paper, right? Like you just report the accuracy values. And but if you're in the real world, you're Amazon or you're a startup, then you have to make sure that your model works. So, and if you're sort of targeting, let's say, healthcare or any one of these other areas where you actually have maybe external customers, then you sort of have inbuilt domain expertise because you have to interact with them and talk to them and things like this. But it'll be interesting to see where this this human in the loop thing goes. And I'm more of an opinion that you, at the moment, you want them integrated in every part of the pipeline. But it's still unclear if that's the right way, that's the right call or not.
Thank you so much, Julius. Rosalind has a question.
Yeah.
I know we're running out of time, but maybe we can take this real quick.
Yeah, sure.
Yeah, let me be quick. Yeah.
So I couldn't hear the first part of your question. It was cutting off. Do you want to repeat?
I think she's having some trouble with the internet. It appears so.
Okay. Or maybe she can like type in the chat.
Thank you for having me. I am a lecturer at the University of Lagos. Okay, you can't hear me?
Yeah,
we can hear you now.
I can hear you guys.
We can hear you now.
I can hear you. Can you hear me? Okay. Yes, I said Julius Adebayo. I said I am of computer science.
I think we lost her. Yeah. Okay. So Julius, you wanted to mention one more thing about. Do you still want to go over it?
Well, I can just say it really quickly. So
okay, no problem.
If I had more time, so the thing that I'm actually more interested, so I'm definitely interested in interpretability and everything.
I got you there.
And everything I've talked about, but the thing that I'm actually more interested in is this, like the lack of data sets to do anything in Nigeria. So the one that I will just mention briefly is, if you have some time, please read this article. So I think it's in FT, or it's in, if you basically sort of type in Nigerian population, blah, blah, if you type in the exact thing in here, this article will come. And the reason why I'm saying this is because I think the Nigerian population, when you look at the figure, they actually say it's 200 million. But if you dig in to actually try and sort of understand this number, like break it down by region and all of these things, I think this number doesn't stand up to scrutiny at all. So in general, I'm very interested in how we can collect more data. So I don't work on this on a day-to-day basis. I work on this other machine learning stuff and writing papers. But if I had to pick what I will actually spend more time on, it would be this. And so if we had more time, I was going to sort of talk about how, like, the problem of lack of data sets, how we can sort of bridge that gap, how we can sort of incentivize maybe local governments or universities. And I was actually going to ask the lady that's a lecturer at University of Lagos what we can do about this. But that's my point. And as to sort of mention is, I was going to ask everyone that's from Nigeria if they know the population of the town they grew up in, and how confident they are that their figure is correct. But we don't have that time. So think if you know what the oh, you're back. Oh,
yeah, sorry, it was network from. Sorry. Quickly, I know time is running fast. I wanted to add this. Working with domain experts is of high value. We can negotiate this because they have the domain knowledge and they will help you so that you pick the right features that will give you the right output. For instance, I'm working on heart data set, trying to predict some coronary diseases. You know, heart disease is #1 killer globally. The data set, I don't understand anything. I've seen the ECG data set. I can't pick the features. I can't pick the why. So this week I'm planning to go and see a cardiologist. So if you don't work with a domain expert, you're going to just mess up your model. So domain expert, working with them is very important from the very beginning. And I want to ask you this, some of the techniques you said, I can relate with them very well because these are some of the things we can use to improve our models, accuracy and performance. I wished you had some implementation showing us this is this, this is this, this is this. Because here it's sweet the way you explain it, but when it comes to implementation, it's another story. I wish you had your code. Is it possible to reach out to you? Because I'm in academics, this is what I do. I want to try out some of these things. Can one reach you by email or something?
Yeah, absolutely. So I didn't include that because I just wanted to sort of do surface high level thing. But do you use PyTorch?
Yes.
Okay, so if you use PyTorch, if you type in Captum, CAPTUM, of course, okay, so we can exchange emails after this, so I can send you the implementations for all of these things. But if you type in Captum, it's a library from the people that actually do PyTorch, and they have the implementations of everything I've talked about here and even a lot more. The library is actually well developed, well sort of standardized. I mean, whether or not you can trust, and I mean, this talk was more about, can you trust the output of those methods? Are they telling you what the model is relying on? Whether or not you can trust the output of those methods is still an ongoing question. I mean, it's in this area, it's like one of the ongoing questions. But I wanted to sort of talk about yours. So I think your point about domain expertise, I'm also, it's like preaching to the choir. I'm completely in your camp, but there's actually a big contingent in the machine learning, in the deep learning community that would say that the reason why deep learning models have performed very well is that we don't need any of this domain expertise, and the model can just learn all the right things that it wants. So I don't agree, but I wish we had somebody like that on this call to sort of, push back on us and make us honest with our arguments. But I completely agree with your point, and happy to, we can exchange emails after this with implementation of all of that.
Julius, we can always invite you back here, right? to give a talk on that. So thank you so much, Roslyn, for that question. And I think I'll just unmute someone now. I don't know who's, okay, yeah, everything is fine. Okay, so we have 2 more questions on the chats. I really would appreciate if we can go through them. I know we are running, we're like out of time, but this
so
is also
I can't see the chat. Is it possible for you to read it?
Okay, I can read it out. So Kelechi asked, was there any uniform saliency change among similar label in the data sets?
Was there any uniform saliency change among some? What does that mean? Meaning, if an input has similar predictions, I guess, can you clarify?
Okay, so his first, okay, maybe he can, but the first question he asked was that how did the saliency map change by layer in the layer by layer randomization? Is there any explanation for difference in saliency similarity across layer levels?
Okay.
Yeah.
So how did they change? So I only talked about one method, which was, I only showed like, where is this thing? So here's like this is what tells you so this is for like inception V3. And this is what tells you how it changes. So some immediately change and then keep changing. And some, so this line is telling, if anything is above this line, that says it's not changing as much as it should be changing. So all of these methods are not sort of changing as much as possible until you get to the lowest level layer. So the thing I can say is that basically the way deep nets are constructed in the lower level layers, those filters, they are very important for learning like edges and sort of low level features. And so what happens is when you sort of reinitialize those features, it sort of messes up most saliency maps almost immediately. But then the sort of folklore is that the upper layer parameters encode more higher level features. So there's less change at the upper layers for methods that don't change, and then there's a drastic change at the end. I should have put a figure for all of these different methods, but I wanted to put this instead. So yeah, but that's a very good question.
Okay. Thanks. I hope that answers your question, Kelechi. Please feel free to unmute if you wanted to clarify the second question. And Choosing Room also asked, "Hi, Julius. My question is whether the effectiveness of some of this debugging method has been observed in the production environment, in a production environment."
That's a very good question. So so the short answer is, I don't know the answer to that. And the reason why I don't is because so first of all, I'm not sure a lot of these methods are being used to sort of assess production models. If you look online, you will see a lot of blog posts and things where somebody trained a model and then they applied one of these methods to try and understand what their model is doing. But I haven't talked to enough so there are startups that say they're helping other companies try and use these methods to understand what the models that some other clients are developing are doing. But I don't know the details of that to be able to know how people are using this in a production environment. So, but my conjecture is that these things have not been used as much as possible. And there's actually a more controversial talk that I could have given that would have said these things are not as effective for debugging. But the short answer is I don't know enough about the production setting. And I think a lot of the companies that are probably using this haven't written enough about, here's a problem that our client had in their model. And we used this saliency map or saliency map X, integrated gradients, blah, 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 to fix it. So there hasn't been enough of those written yet. So, but I wish I had more examples, but I don't know.
Thank you, Julius. So maybe you continue with the population and then
No, I'm done with my rant on that. So
okay.
Basically I was going to that's my talk, that we need more data sets, and I wish I were working on that, but the honest truth is I'm not working on it. But I think it's a very important problem, and it's maybe even arguably more important than developing the model itself. So I was going to use this population example as a way to try and figure out how much people know about like where they grew up and the population of where they grew up. And I played this experiment on Teju earlier, and she didn't quite pass that test. So so I was going to play it on everyone else. But basically my point is that lack of data set is a problem, and then the population is the estimating the census and estimating the Nigerian population is one example of where that issue is actually well demonstrated. So if you have some time, please read this article. It's a very good article. I don't know the author, I don't know the person that wrote it, but it's a very good article, and it's something that hopefully we should all work on more. And that's pretty much my point on that.
Thank you so much, Julius. Yeah. It's been fabulous having you here this evening for me and morning for you. And I hope that we get to have you back here sometime soon. And if you have any question for Julius, please feel free to reach out to him on Twitter. What's your Twitter handle?
So actually, if you want, so my email is actually my first name dot my last name at Gmail. So Julius.Adebayo at gmail.com. So you can just send me an email from there. I would type it in the chat if I had more time. But it's like all lowercase Julius.Adebayo@gmail. And Twitter, I think it's Julius_Adebayo. Though Twitter, my Twitter is not really as interesting as I mostly just retweet basic stuff. But yeah, Twitter is Julius_Adebayo. But email if you want to sort of, and if you want the slides or if you want references to implementations and all of that stuff, Julius.Adebayo@gmail.com.
Okay, so thank you so much. And please feel free to reach out to Julius. He's an amazing person, as you can already tell. And thank you so much for joining today's talk. And we hope to see you again in future talks. You can access the talk again. It's currently on YouTube. We're recording it, so you can go back. If you want to rewatch some part, just go back to it and, feel free to interact in any way. And I'm always on Twitter or so as Teju Afonja as well. ASS Lagos. You can also reach out to us on Twitter or on email. So thank you, everyone. Have a good rest of the day.
Thank you so much, Julius. Thank you.
Yeah. Bye.
Bye-bye.
Teju, love you.
Thank you. Love you too. Bye-bye.
Bye.